Taking space for Riemann surfaces using Fuchsian group. And we said that we are defining the Teichmuller space by referring to a particular Riemann surface R, and this is the base space. Now, corresponding to the Riemann surface R, we have a Fuchsian model H by gamma. So we said that we could identify this with the Teichmuller space with the space of inequivalent Fuchsian groups, which provide you Riemann surfaces with H number of handles and N number of punctures. So then our aim was to make this characterize this space. So we said that the Teichmuller space can be characterized by using the notion of quasi-conformal transformation. A quasi-conformal transformation changes the complex structure. I said that these are general transformations that preserve the orientation. So you get a new domain d tilde that has same orientation as D. So that's the only condition that we wanted. Now the space of all inequivalent so assume that you have a Riemann surface R, then you consider set of quasi-conformal transformation that you perform on R. The space of all inequivalent such quasi-conformal transformations can be identified as a Teichmuller space for Riemann surface with some specific number of specific topology. Then we said that you could for each quasi-conformal transformation we can define the Beltrami differential as with a particular quasi-conformal transformation. So this transform is a -1 differential. Okay. This is fine. Yeah. So this transform as a -1 differential, and we want that when you define such we are defining the Beltrami differential for a specific Fuchsian group gamma, right? Since we are defining the quasi-conformal transformation or the Beltrami differential for a particular Riemann surface. That means the Beltrami differential, the -1 differential that we are defining on the upper half plane should transform as a -1 differential with respect to gamma. So that means mu should transform appropriately. Once you have such a mu, you can reverse the whole problem. We say that you start with such a Beltrami differential that transform under gamma appropriately, and then you could solve the differential equation del f by del c bar equal to mu f or mu del f by del c. So you can solve this differential equation and obtain several solutions.
Sorry, why with respect to gamma?
Because you are defining the differential on the Riemann surface R, right? So we said that mu should be related to mu of c with some factor. That tells you it's a -1 differential, right? And then you take that mu and solve this differential equation. You will get several solutions, and if you take a particular solution that satisfies the normalization condition f of 0, f of 1 equal to 1 infinity, you obtain a unique solution, and that unique solution is canonical quasi-conformal transformation associated with differential mu. So that means for the space of all quasi-conformal transformation can be associated with the or can be identified with the space of Beltrami differentials. But all Beltrami differentials won't give you different complex structures. So assume that you have a Beltrami differential mu that transform with respect to gamma on the upper half plane, and then you have a another Beltrami differential nu that again transforms with respect to group gamma. Then we ask the following question: when mu and gamma are equivalent, are producing the same complex structure. So to define that, we said we have to take mu and nu and then solve the equation, or we could start from mu and nu and then define an extended Beltrami differential on the whole complex plane. So you have mu c on the upper half plane, 0 where c is on the complement of upper half plane. So you can solve this equation. So now you have a new equation, del f tilde del c bar equal to mu tilde del f del c. So again you can use a normalization condition and find the associated f tilde mu and f tilde nu. Then the statement is that mu and nu produce the same Riemann surface only if f of tilde mu c is equal to f tilde nu c whenever c belongs to the complement of upper half plane. So this was a condition. So this equality tells that mu and nu are producing the same Riemann surface. So that was a statement. So now you can take
Is everything holomorphic in the lower half?
the Beltrami differential equation seems to suggest that they are holomorphic, right?
That's what you're
Yeah. Now you can take this object and then compute the Swashing derivative on the lower half plane. So take f mu tilde c and then find the Swashing derivative. So I gave you the definition for Swashing derivative yesterday. So you consider this Swashing derivative. That Swashing derivative transform as a quadratic differential in the lower half plane, right? So this is it's easy to check that f mu transform as a 2-0 differential with respect to gamma. Since f tilde mu is same, f tilde mu and f tilde nu are same on the lower half plane whenever mu and nu are producing the same surface, we can say that the space of such quadratic differential is the space of or we can identify the space of such quadratic differential as the Teichmuller space for Fuchsian group gamma. So the space of all quadratic differential that we define this way on the complement of upper half plane. This is what we identify with the Teichmuller space for Riemann surface. Since this is a space of quadratic differential, we can use Riemann-Roch theorem. So once you use Riemann-Roch theorem, that tells the dimensionality of this space. So you have the space of quadratic differential whose dimensionality you can compute using the Riemann-Roch theorem. That says that for a gamma that representing genus H Riemann surface with n punctures, such a gamma has an associated space for quadratic differential and the dimensionality is 6h minus 6 plus 2n. So, and this is precisely the dimension of Teichmuller space. This is the way we compute the dimensionality of Teichmuller space.
What does the Riemann-Roch theorem say in this context?
So in this context, I mean, I don't want to get into the full details. It's related to the divisors for quadratic differential. So the ultimate statement is that we can compute the individual, the number of independent basis vectors that you require for generating the whole space, right? That means that's the dimensionality of this space. So the dimensionality of this space is actually 6x minus 6 plus 2n. Since we identified this space with the Teichmuller space, this says that the dimensionality of Teichmuller space is 6h minus 6 plus 2n.
Pi mu z being 2-0 differential up to this point, it's okay. Then what was the definition?
So this says that, so this is a space of all such Beltrami differential, all such quadratic differential. I'm just saying that you can generate all you take all Beltrami differentials that transform under gamma, compute its f mu with this normalization, right, and then compute the Swashing derivatives and then say that all such quasi-conformal transformation provide you.
Differential was defined through F.
Yeah. Now, to start with, I said that I am inverting the problem, right?
Yeah.
So once I invert it, I can start from Beltrami differentials, solve the equation.
Any -1
yeah.
form
Yeah.
under gamma.
Yeah.
I see.
So this is the procedure. You extend it to the full complex plane, and then solve the equation. Use the normalization. Even if you forget to use this normalization, it's okay, because so the solutions, the different solutions of mu are related by the global symmetry of complex plane, right? So they are related by Mobius transformation. The good thing about Swashing derivative is that if you apply Mobius transformation, that just filter it out. They won't really appear for the that. So let's start with f tilde and some f bar. Those are related by say some Mobius transformation. When you put them into the Swashian derivative, the Swashian derivative provides you 0 for the Mobius transformation part. So that's why this space is much less than the space of all possible quasi-conformal transformation. So this is a filtering process. This filters out many unwanted quasi-conformal transformations. So you are taking
statement of T in a two-atom tensor being a tensor under the
yeah. That is true. That is a statement. So there we have this. We are computing the. Yeah, that's true. So the statement is the following. So you identified the Teichmuller space with some quadratic differential space. Then you can use Riemann-Roch theorem, compute its dimension. So you want this many number of tangent vectors if you want to construct the differential top form that give you the string amplitude. So now the statement is the following. So since you identify T with H2, see, this is a space that you define on the lower half plane. So you can consider the Riemann surface H by gamma by moding out gamma with respect to the upper half plane. Now you can do the same thing for the lower half plane, H star by gamma. So what you obtain is, here if you obtain Riemann surface R, here you obtain the image of the same Riemann surface with the anti-holomorphic coordinates as the complex coordinates, holomorphic coordinates. So this is just the inverse of this space, right? So you obtain a space of quadratic differential on the image of Riemann surface R. So that's a nice thing. Now what one can do is, you can try to convert this object into an object on the Riemann surface R.
Can you mention about the complement of the upper half plane?
Yeah.
You really mean the lower half plane?
I mean the lower half plane here for this case, right? I don't include the real line. When I say H star, it doesn't include the real line. So this is so the point is that you constructed a space on the image of Riemann surface R. To make that space on the Riemann surface R, what you have to do is you have to just take the complex conjugate, right? So you can take the complex conjugate of phi mu z. So then here C belongs to the Riemann's upper half plane, and then multiply this with the factor -2 imaginary part of C whole square. Then it's easy to see that this transform is a Beltrami differential, and this Beltrami differential mu phi. So all such Beltrami differential form a space, and that space is known as the space of harmonic Beltrami differentials. The good thing about space of harmonic Beltrami differential is that you can identify the space of harmonic Beltrami differentials with the Teichmuller space gamma, T gamma. So you found a region inside the space of all Beltrami differentials, and we call that's a space of harmonic Beltrami differentials. Then that space of harmonic Beltrami differentials is exactly the Teichmuller space. Now you have a space that is defined on the Riemann surface R itself, not on the image surface, right? So you have this object is defined on the Riemann surface, or this object is defined on the upper half plane, not on the lower half plane. and such Beltrami differentials provide you the Teichmuller space.
But when you say harmonic,
Yeah.
what is the
Yeah.
special meaning that is they are all solutions of Laplace n equal to 0?
So you can compute it, then find it.
Well, harmonic do you mean? Because normally in complex variable.
So for this moment, for us, since I have given you how to compute this object, I mean, I don't have to really explain why this is called as harmonic Beltrami differential. I'm not going to spend time for that nomenclature. I'm saying that the space of all such differentials can provide me the Teichmuller space.
But they are harmonic also.
They are harmonic, actually. They are harmonic.
Because not all
Beltrami differentials are satisfy that particular thing, right? For any f. So see, this is actually a filtering process. You start with a random Beltrami differential and then somehow go through all this procedure. By solving a differential equation, you are finding a subspace in the space of Beltrami differentials that can be identified with Teichmuller space, which is actually a nice thing, right? So we are actually throwing out all the null vectors.
May I ask you, is that harmonic nomenclature has something to do with the traditional differential geometry?
Yeah. So actually, so you could figure out this by doing the full path integral, which you see in Polchinski's book. So these are solutions of some differential equations. So that's why they are called as harmonic. But I mean you don't do any explicit construction. So why I do this? So I do this just to really construct something explicit. So here is a recipe. I'm just giving you a recipe that provided I have some particular bunch of specific quasi-conformal transformation, I'm telling you how to compute the associated harmonic Beltrami differential. And this is going to be useful in the next section.
What I'm bothered about, you have not mentioned anything about the topology.
Yeah, I have mentioned that when I specify gamma, that specifies the topology. Yeah.
Okay. So unless there is some homotopy, nothing will. There is no point in doing this.
Now, for me, first of all, this is not a abstract. I mean, rigorous.
I'm worried about that.
Then just don't worry about harmonic. Just say that this is a space of this is some random space, say space H or some space F. So I'm not going to spend much time on that harmonic part. This what you are saying is true. One can really study that, but I mean that will just take away some time. And we won't that understanding won't be really useful for whatever I'm going to do next. So I just want to give you a recipe for computing or constructing the Teichmuller space. That's what I promised you, right? So when I started, I said that what we want is we want a better understanding how to construct. We should know how to construct Riemann surfaces explicitly, and we want to know how the space of all inequivalent Riemann surfaces can be characterized. This is my final answer. So you do all these things, you finally construct the space of all inequivalent Riemann surfaces.
I knew what is just a complex conjugation.
Yeah, it's just a complex conjugation. So now, given that, what I gained is a space of all inequivalent Riemann surfaces. So once I have the space of all inequivalent Riemann surfaces, I can study the tangent space on it, right? Harmonic Beltrami differentials that transform under gamma. So say you have this space, which is equivalent to T gamma, Teichmuller space. Now pick a particular point. Now you can choose a curve on this, right? So that means you are making a curve is parameterized by one parameter t. That could be complex or a real parameter. So you harmonic Beltrami differentials and fix the point t equal to 0, then take a derivative with respect to t. That provides you the tangent vector, right?
Is it phi mu or mu phi?
Mu phi. Mu phi. My phi mu is a space of quadratic differential. Mu phi is Beltrami differential space.
So I didn't get a nomenclature here. So what is this curve?
So you have a space t gamma. Now in the space I can consider a right?
This family is being labeled by what?
A parameter t, right? So that provides you a curve. Now I want to find a tangent vector at some random point, say t equal to t0.
And mu phi means that you are considering a harmonic.
Yeah, that is true. So then what I should do is I have to take, I just go to that particular point in the curve and then just compute the rate of variation, right? At that tangent vector at t equal to t0, right? Now I can consider all possible independent curves on it, right? That means I am constructing the tangent space at a particular point and then finding all the independent basis vectors. Exactly. I can see that I can construct 6h minus 6 plus 2n number of independent basis d by dt, which I denote by, say, nu t, say, or nu t.
So,
nu t0, right?
phi, I'm confused about this. Mu phi is the Beltrami differential corresponding to phi.
Yeah.
That satisfies that equation with a space by.
Yeah, that's true. So you see that you can explicitly construct the tangent vectors or the tangent space of Tek-Muller space at a particular point, right? And now why we are interested in this? Now we wanted to construct a differential form on the Tek-Muller space, right? Or on the moduli space. So to construct a differential form on a space, you should know what are the tangent vectors at any point on that space, right? This is the basic thing that you want if you want to construct a differential form. In simple language, that means you want to know how many independent directions are there, right? Only then we can define a differential form. So that's what we want. So to do that, now since we have this explicit space and we know how to construct the tangent vectors, we can directly go ahead and then define the string measure. Is given as follows. Oh, actually, the string I introduced them in the first lecture. I motivated why I should study these things, and I had a specific goal for studying this. I mean, I started from the basic principles of string theory, then found that I have to study Riemann surfaces and the space of all unequal Riemann surfaces. In the first lecture, right? So maybe I can briefly have n number of string scattering, and then each string identified with or characterized with some number of quantum numbers a1 to an. And each AI contains information about the spin of states, the state, and the momentum. So whatever quantum number is required, you can specify using the index an or AI. Then that means, so you want to study the scattering of n strings. Final form is given as a sum over number of loops, just like in quantum field theory. So we introduce a parameter coupling, a closed string coupling constant, and then you take this GC and then consider the hth power. Then we said we can organize the string amplitude into sum over different number of handles, and each term can be thought of as a contribution to the full amplitude coming from a particular loop. And then we said how we are going to compute Yeah, this contribution AH.
You are considering this matrix of
Yeah, so we are considering actually the interaction string amplitude. String amplitude. Yeah. So in the so you are considering the particular scattering process, and then you want to compute the associated amplitude, which in general is not exactly equal to the scattering matrix, unlike in the case of quantum field theory. But we can construct the scattering matrix from this object. So now we said this object AH, A1 to AN, can be understood as a moduli space of Riemann surfaces with h number of handles and n number of punctures. And we want the whole thing that we were trying to do was to construct the moduli space of Riemann surfaces. Now I'm going to tell you what exactly is the explicit form of FH, this particular top form. So I always keep. And this form can be written down as a path integral expression. So let's say you choose to you choose a particular parameterization of Teichmuller space, which I denote by M1 to M6h minus 6 plus 2n. Associated with the Mi, you have nu I. Then the string measure Fh A1 to An is given as a path integral of over dx mu. This is embedding coordinates, and then path integral over ghost field dc, db, dc bar, db bar. There's the multiplied with a phase weight factor e raised to minus s, sgh. S is the Polyakov action, and this is the action for B, the field. Now, since you have n number of external states, you have to impose some boundary condition for the path integral. Using the state operator correspondence, you could think of that boundary condition as a particular operator in your theory. So which is denoted by VA1 to VAN. So this represents the boundary condition for the path integrals. Here you have a path integral, and this represents the boundary conditions. And now you have to insert the part that generate the string measure. So you have a multiplication running from 1 to 6h minus 6 plus 2n. And here you are using the tangent vectors that you constructed.
M's are the
Coordinates on the Teichmuller space.
U's are the tangent vectors.
Associated tangent vector. Right? So here, associated to a parameter or a coordinate t, you had a tangent vector nu, right? Nu t.
At every point you have that number
6x minus 6 plus 2n number of independent tangent vectors at a generic point.
At a generic point.
Yeah.
The coordinate of that generic point is given by M1.
M1 to M6h plus
So
6h minus 6.
at that point, mu I are the components of the tangent.
Exactly.
So logic is that you have integrated overall matrix, and then you show the integration of matrix is the integration of
Complex structures.
and therefore integration of Teichmuller.
Yeah. So here I will explain what does this symbol means. So here I introduced a new symbol, nu j b. What is this? We know that b is a quadratic differential, right? BCC. This transform is a quadratic differential.
How exactly those P's are the online?
Visa. Oh, so that I mean, for that you have to go back to the basics of path integrals. So in path integrals, we know that any boundary condition for that you impose on the path integral can be thought of as a condition that is generated from a particular operator. Huh? So there, I mean, this is a statement which is true in any dimension. In any dimension path, so to make it, if you want to compute it explicitly in 2 dimension, things are easy. That's the only thing. You can use the complex analysis to do that. But in general, this statement is true.
Some boundary condition in the differential. So when you are integrating over dx, you have to put in some.
So those boundary condition you can generate using an appropriate operator. So depending on, I mean, in that case your operator may not be inserted on a particular point. It may be a extended operator, right?
In general, it's a non-local.
Yeah, in general it's a non-local operator.
Local operators in
Conformal field theory.
Put it anywhere in the surface.
Exactly. So that's the place where you are using the conformal symmetry. Otherwise, this is a statement that is true in any theory, right?
You won't call a non-local operator really an operator.
I mean,
Let's focus on the part that is going to tell us.
yeah. So here, so I introduce this object, and I am trying to explain what do I mean by this notation. So, to first make the observation that BC can be thought of as a quadratic differential on the Riemann surface. Since CB system itself is a ghost field, that means CB are actually bosonic, though they are anti-commuting. And so, since it's a bosonic operator, you can think of this as a differential on the Riemann surface, and the transformation properties of BC tells that it's a quadratic differential. Now you have a quadratic differential here, which can be denoted as 2,0 object, and you have a Beltrami differential here, which is a -1 operator, right? So when I multiply these two, you have to just add the signatures, right? That means you have a 1,1 operator, or 1,1 object, 1,1 differential. You can integrate a 1,1 object, right? 1,1 differential, DC bar. You can integrate DC bar over the whole Riemann surface. So this pair, this is an inner product between B system, B field, and the tangent vector, and this is defined as dx in integral of dx dy with BC insertion and nu j insertion, and this is supposed to be integrated over the Riemann surface, or equivalently over the fundamental domain of Riemann surface in the upper half plane. So this provides you a pairing between B field and the tangent vector. So now what? See. So this is the z equal to x plus I y. Fundamental domain corresponding to the Fuchsian group gamma, or the domain that represents a Riemann surface R. Oh, I had the reparameterization ghost, right? Yeah, that's a B. So now you observe that you have tangent vector here and the B field here. So now if I look into this product, if I swap the ordering of this product, it acts like a differential form due to the fact that B is anti-commuting.
The tangent vector is in that space.
In the Teichmuller space.
Is there
So both of these objects are defined on a Riemann surface, right? See the beauty of the whole construction is that you define the tangent vector as an object on the Riemann surface, and the quadratic differential that you have is again an object on the Riemann surface, so that you can multiply them and integrate over the surface, right?
What is the basis of
The tangent space, right? So this object, you can easily check that this transform as a differential, a top form on the moduli space or on the Teichmuller space.
And this is basis independent because there's a determinant.
Which one? This one.
This whole object, this pi, is a basis independent.
Yeah, you can check it. It transforms as a top form.
Which one?
The whole multiplication. Right. Yeah. The object nu is a commuting object, but the field B is anti-commuting, so that the total object acts like a DMI, and then I have to multiply each piece with delta Mi. So this multiplication, this object together with delta Mi provide you the DMI. So that's the way you construct differential form on the moduli space using string theory principle. So now this object after the path integral provide you the top form. So this particular piece can be thought of as an operator valued differential form of the Teichmuller space. Only when you evaluate the correlation function you get an object on the Teichmuller space, right? So this can be thought of as a operator valued differential form, and then the path integral can be thought of as inserting this operator inside a inner product, inside a CFT inner product. So this is the way you construct differential form in bosonic string theory. And this definition is unique. You don't have to introduce any further normalization. So this has the appropriate factorization property. So in string theory you never have to do any normalization. Everything is first principle construction. So now we go to the next topic. We constructed a differential form on the moduli equality on the Teichmuller space.
This is any conformal
yeah, exactly. So here
this integral dx mu which is minus s can be replaced by
any matter conformal field theory, right? I could even replace, I mean naively I can try to replace it even with superstrings, but there are some additional complications which I will explain now.
Okay, so there is V vertex operators will also have closed part. That is not playing any role.
Actually those parts,
They
I
are
mean,
playing some role. Closed parts also have some geometry. Riemann surface geometry.
actually that's here.
Oh, so these are only matter parts.
Yeah.
So this is just V.
So you had two kinds of vertex operator: integrated vertex operator and unintegrated vertex operator. When you do calculations on sphere with some number of punctures, you usually play with the integrated vertex operator, which is easy to handle.
-3.
Yeah, so it's easy to handle, but they won't deal the spurious pole. You can't use them to understand the IR divergences. It's very hard to understand the IR divergences using integrated vertex operators. They don't come with the proper regularization. Whenever two integrated vertex operators collide, then you have infinities. You don't know how to really handle them. So that's why you can think of scattering process computation in the tree level as an integration over the places where you insert vertex operator, right? When you use a complex plane and then integrating over the locations where you are inserting the vertex operator, there you are thinking that the vertex operator that you are using is an integrated vertex operator. So the puncture you are thinking as a mark point, not as a genuine moduli. So then you allow them to collide, which will provide you some infinities. So it's very hard to deal with IR divergences if you are using the integrated vertex operator picture. So then in that situation you won't see such pieces. So you are dumping all such pieces into the vertex operator, which is actually not a precise thing to do. But the calculation that you see in Polchinski is not done in this way.
Exactly. So there what you do, you have actually, even if I try to do four point scattering,
Yeah.
so here you're doing it a bit different way. Here you're fixing it to eta,
Yeah.
and then instead of integrating over eta, you are doing it in a different way. Could you explain in the simple case like what it should be? Like 4 point on a sphere?
Yeah, 4 point on a sphere. So the usual calculation is that fix 3 points and then integrate over the 4th point, right? So this is what you do. Now what I would suggest you to do is you have to use the proper. You should understand what is the moduli parameter for this surface. I mean, this is one way of doing it. So where you are thinking of the puncture as a mark point. Now you can think of puncture as a genuine moduli, not just as a mark point. Then you have to use something like Finchel-Nielsen coordinate or some other way of parameterizing the Riemann surface, right? And then so that I will explain next. So that's yeah. So anyway, you have to. I mean, this is a proper construction of differential form in the Teichmuller space using string theory principle. So if you want to construct string measure, this is how you are supposed to do. All other treatment are naive, and which will fail in some situations. So it's very hard to study the factorization properties if you are not constructing the differential form in an appropriate way. So which is an important thing to do. For example, if you want to construct, if you want to find the Feynman I epsilon regularization, then thinking of the fourth puncture as a moduli make things a little complicated.
But I want to ask you another question. So if you have like, so you're now also talking about loops, that's what I'm saying. If you have a field theory calculation loops, you know there can be higher divergences using massless particles. And because field theory is some limit of string theory, it should also appear in the string. So the higher divergences should be there in the string.
That's true.
IR, that you wanted to avoid higher divergences.
No, IR divergences is there even in quantum field theory, but you don't want infinity there. You want to regulate it. That's why you go off shell, right? You go off shell, regulate them, and then when you compute the scattering amplitude, it's not the naive amplitude that you compute, right? You have to appropriately take the 1pi part and then resum everything to take care of the renormalization, right?
This is an analogous thing here because you cannot go off shell here.
We can go off shell here.
You will explain that.
Yeah, I will try. That's why we have to use string field, do string field theory.
But at least in the way that you have written, I don't see.
So this one is not an off-shell object. This is an on-shell object. So that means VAI has some particular conformal dimension.
So you're just reformulating the standard textbook thing in
It's actually this is a standard textbook thing.
Well, for the 4 point, I don't know. I haven't seen such a thing.
Actually, for the endpoint and H loop, this standard thing is there in Polchinski. So this is something which is already known, but I am saying that, so in Polchinski he just says that if you have all such spaces, I mean this is how you are supposed to construct it. Now what I say is that how you will construct all this object, the tangent vector. You have to construct this tangent vector explicitly. Only then you get the explicit string measure, right? This is.
I was asking something different about. My confusion was regarding a statement that maybe you don't want higher divergence.
That is true. That it should be there. It should be there, but the point is that you don't want to evaluate 1 by 0, right?
That's right.
You want to slightly go away from 1 by 0. You want some regularization. If I'm using a mark point picture, then it's difficult to regularize things.
So you're saying using this kind of picture, you can go off shell easily. You will explain that.
Yeah. Even with the other thing, you can go off shell, but regularization is slightly difficult. I mean, you have to choose some very complicated contours in the moduli space. Yeah.
I have a simple question. This product over J, this part is only ghost thing?
Yeah. So the ghost thing is the one which is important for constructing the measure part. I mean, again, matter is there in the vertex operator and the action, right?
So these are ghost number 0 operators. These
V. You mean?
No, VA1 to VA.
Yeah.
Those are ghost number 0.
No, actually they have some ghost number, right? Because B has some ghost number. The total object should not have any ghost number, right? It may have some C factors.
So they are ghost effects.
Yeah. But when I change the DMI, I should get anti-commuting property, right? Only then I can think of this as a differential form. So anyway, this is the way we are supposed to construct the string measure. Now the next question is to understand how I can integrate this measure over the moduli space. Right? I just discussed to you about Teichmuller space. I didn't tell you how you get moduli space out of from the Teichmuller space. When I defined Teichmuller space, I said that I am using quasi-conformal transformations that can be related to identity, right? So all those quasi-conformal, I only consider all those quasi-conformal transformations that can be related to identity, but there can be quasi-conformal transformations or transformations that can't be related to identity. So those are the large diffeos. I didn't take care of large diffeos. So large diffeos are there in the Teichmuller space. So 2 points in the Teichmuller space may not represent inequivalent Riemann surfaces. 2 faraway points in Teichmuller space may represent same Riemann surface. So those points can be related by a transformation. So say you have Teichmuller space, 2 points in the Teichmuller space you may be able to relate, and that such relations form a group. So that's the mapping class group, MCG.
I thought Teichmuller space is all inequivalent stuff. All the points are inequivalent subsets, right?
Inequivalent?
Discrete. Yeah, I thought these are all inequivalent. What is this discrete coming from?
I said that to define Teichmuller space, I am using only quasi-conformal transformation that can be related to identity. But in a simple term, that means I am using only diffeos that can be related to identity. There could be large diffeomorphisms. Those I didn't take care when I defined my space of unequal Riemann surfaces. So I forgot, or I didn't include some of the identifications, right? So those identifications form the mapping class group. So that means you say you have a torus, you can define A cycle and B cycle, you could perform a diffeo, large diffeo, so that A cycle become B cycle, right? Those kind of transformation I didn't take care when I defined my Teichmuller space. So that means even within the Teichmuller space you could find 2 points or 10 number of points or infinite number of points that can be related to each other. Or in other words, infinite number of points in Teichmuller space may correspond to same Riemann surface. And the good thing is that those points are connected by a group transformation which act on the Teichmuller space.
But you said every point in the Teichmuller space is a different complex structure.
Yeah, but
Given that if I define inequivalence using the quasi-conformal transformation, that can be related to identity.
These are the essential C and the torus.
Torus. So I didn't use the large diffeos. Still there are leftover diffeos.
Okay. So this is the SL to Z remnant term.
Exactly. So you have to take Teichmuller space T gamma and mod out by MCG group to get the moduli space. And I am supposed to integrate the string measure only over M gamma or MHN. So I said I know how to characterize Teichmuller space, but when I finally go back to string amplitude, I see that it's not T gamma I am supposed to deal with. I am not supposed to deal with Teichmuller space. I am supposed to deal with mapping with the moduli space. So I should know how to find a fundamental domain inside Teichmuller space with respect to the mapping class group. So this is something which I should know. So I should know what is a mapping class group, and then I should know how mapping class group is acting on the Teichmuller space, so that I will be able to find a fundamental domain inside the Teichmuller space that represents the moduli space. So this is one problem that I have to address if I want to evaluate string amplitudes. And the second problem is that if I want to go to say superstrings, in superstring theory we don't have Riemann surfaces. Actually we have super Riemann surfaces. Our world sheets are not simple Riemann surfaces. So we have a surface with complex structure, then we say that that's a Riemann surface. If you have a surface, if you have a two-dimensional surface with one more structure, say super conformal structure, then we say that that's a super Riemann surface. I am not going to discuss in detail about a super Riemann surface, but the statement is that world sheet in superstring theory has more symmetries, so that the space of all super Riemann surfaces or any super Riemann surface can be parameterized complex coordinate C bar and odd coordinate theta bar. So this is a commuting coordinate, this is an anti-commuting coordinate. That means you have further structures on your surface. You can consider such Riemann surfaces and then study the space of all inequivalent super Riemann surfaces. And that give you a space which we call a supermoduli space. Space of all inequivalent Riemann surfaces is the moduli space. Now once you introduce new structures, you get supermoduli space, and the supermoduli space is parameterized by some number of anti-commuting coordinates. So there I can again define superstring amplitude using the similar ideas. One can construct the super Beltrami differentials and then define a appropriate ghost fields, super ghost fields, which are given by B equal to B field plus theta into some beta field. So B is a commuting boson, anti-commuting boson, and beta is a commuting fermion. So you have to introduce new reparameterization ghost that take care of super reparameterization, and then you can use this capital B.
What do you do? B equals B to
B plus theta into beta. So I am defining a new
plus theta beta. Okay.
Yeah. I am defining a new I can define a new ghost field on the super Riemann surface, and then construct the super Beltrami differential, and then define a measure on the supermoduli space, and then I denote it by f as h, and then I am supposed to integrate this object over the supermoduli space. So that means I am supposed to integrate over odd coordinates, commuting coordinates, which I denote by dmi's, and over odd coordinate d theta is. Now the main challenge is to integrate out this odd coordinate, right? So we know that odd coordinates are anti-commuting, so it's easy to integrate them out. So naively you can go ahead and then try to integrate them out, and then your goal is to obtain an integral over moduli space with some appropriate measure piece which you obtain from the super measure. So you want to integrate out the odd coordinates and obtain a object on the moduli space. Unfortunately, you can easily see that it's very hard to distinguish between odd coordinates and even coordinates, because if I take two odd coordinates and multiply them together, they transform like a even coordinate, right? Their parity is even. So I can start from an even coordinate mi, and then shift it to mi plus theta j into theta k. This is a new commuting coordinate, right? So it's very hard to distinguish between what do you really mean by even coordinate and odd coordinate. So this is a serious problem. So when I try to integrate naively by saying that something is odd coordinate and then just perform the integration, I get an answer. Now I say that no, that's not the odd coordinate, or
a type of supersymmetry transformation.
You can think in that way, but you could naively say that I can always define even coordinate by shifting the even coordinate that you gave me by adding with us a pair of odd coordinate, right? So by using anti-commuting coordinates, I can construct a commuting coordinate, right? If I multiply theta j and theta j, I get 0. But multiplying theta j and theta k won't give me 0, right? So whenever the dimensionality of odd coordinates is more than 1, I'm bound to have some ambiguities, right?
But then it is like a translation.
Yeah.
Right?
Yeah.
So you could ask this question in the bosonic case, right? When you give a translation to those moduli space coordinates.
The measure that you constructed is invariant under such translations. Right. So
also that invariance will be there.
It won't be there. So that's broken. So that invariance you don't have.
So okay.
So So it gives one answer for one choice of odd coordinates, and it gives some another answer for some another choice of odd coordinates, or the
undo it by from the super.
Yeah. So you don't have the symmetry, right?
There is no transformation on the odd.
Yeah. I mean, you could try. So you can start from theta I, and then theta I plus some c, some mi, theta j. This is another odd coordinate, right? So there are so many ambiguities in defining what you really mean by commuting part of the moduli supermoduli space and anti-commuting part of moduli space. So
Direct product.
they are not actually direct product. In normal supersymmetry, we always integrate out the anti-commuting coordinates, right? We say that okay, there is a unique way of defining even coordinates and odd coordinates there, right? Why? Because you have a rigid superspace. So in the case of superstring theory, the supermoduli is not a rigid superspace. It's actually a supergeometry. So it's very hard to distinguish between what you mean by odd coordinate and what you mean by even coordinate, right? So in usual geometry also, it's very hard to distinguish between different coordinates because you always have diffuse, right? But when we have such situation, we integrate out all coordinates together, right? We don't try to separate out some piece and then decide that that is the final answer that we have. So here what we are doing is precisely that thing. We want to break that symmetry and then say that this particular piece are the odd or anti-commuting coordinates, and there is another piece that corresponds to commuting coordinates, and keeping that itself is fine. Now what I am doing is I am just integrating out one piece, right, which is basically breaking some symmetry, right? That means if I use symmetry to transform from the initial state, I get another answer if I choose some another set of anti-commuting coordinates. So we have some difficulties there. So that means you can't think of supermoduli space as a product of moduli space into some anti-commuting space. So that's a difficulty. Now for a moment, forget that there is some such difficulty. You can go.
In the usual case of description of a manifold,
Yeah.
you have a set of points,
Yeah.
and then you have coordinate charts,
Yeah.
right? So
Yeah.
coordinate charts, you can there is an ambiguity in that
Defining.
of that,
Yeah.
right? But you could do an integration over a subspace
Yeah.
of the manifold itself,
Yeah.
which has an invariant meaning.
Yeah. No, you don't have an invariant meaning there.
I do have an. It's in coordinate independent state.
So if I break some coordinates,
Yeah.
if I split the coordinates into two,
some subspace of the manifold.
that is
So
true.
you are saying there is no manifold. You cannot define some supermanifold.
No, you can define a supermanifold.
Part and then
Yeah, you can define such a supermanifold, and then
is there an coordinate independent way of describing
so
what you want?
that is true. So how you do that? To do that, whenever you have such complicated space, you decide that okay, don't try to do integration over the whole moduli space or supermoduli space. Let's consider patches. Right? Each patch you can define a set of commuting coordinates and anti-commuting coordinates. Then integrate out anti-commuting coordinates in each patch. Integrating out an anti-commuting moduli provide you a particular operator on the Riemann surface or on the world sheet. So whenever you integrate out a odd coordinate, you are introducing you should introduce an operator on the world sheet, and that operator is known as the picture changing operator. So each DCI integration provide you the associated picture changing operator. Now if we choose say in supergeometry, unlike the case of Riemann surfaces, in super Riemann surface you can have two kinds of punctures, or actually there are many possibilities of punctures. In Riemann surface case, when I introduce a puncture that generate a moduli, one particular moduli parameter for the surface, right? So whenever I introduce a puncture, that increases that makes the size of moduli space larger by introducing a introducing one more dimension in the moduli space, right? But when I have a super Riemann surface, if I introduce something called an NS puncture, that increases the dimensionality of moduli space by 1, and whenever I introduce something called a Riemann puncture, that increases the dimensionality of moduli space or supermoduli by half. So that means I can't introduce a single Riemann puncture. I must always introduce Riemann punctures in pair. I can only introduce even number of Riemann punctures on a super Riemann surface. So that's why we have more complicated situation in the case of super Riemann surface or in the case of superstring theory. So now you can try to integrate out coordinates in each patches. Since there are 2h minus or 4h minus 4 plus 2nns, where nns is the number of ns punctures, and say there are nr punctures. So this is the dimensionality of supermoduli space of genus H, super Riemann surface with ns number of ns punctures and nr number of Riemann punctures. So you have the supermoduli space and then choose different patches in the supermoduli space, and in each patch you define 4h minus 4 plus 2 nns plus nr number of odd coordinates. Integrate them out. That means we are supposed to introduce this many number of picture changing operators on the world sheet. And then in another patch, again you have to perform the integration over the moduli space over the odd coordinates, and then introduce this many number of picture changing operators. So depending on how you choose your odd coordinates, the way you are supposed to distribute picture changing operators differ. That means over the whole supermoduli space, you are actually when you choose a patching, or when you choose different domains in the supermoduli space, that corresponds to choosing a bunch of different domains in the moduli space, right? If I go down from supermoduli to moduli space. So this procedure means that when you are computing superstring amplitude, you are supposed to start from moduli space. Say if you don't want to work with supermoduli space, how will I do superstring theory? So I can start from the moduli space and then split the moduli space into several pieces, and in each piece I can introduce 4h minus 4 plus 2ns plus nr number of picture changing operators. So by introducing this many operators on a point in the moduli space, I mean each point in the moduli space corresponds to a particular world sheet, and on that world sheet I should choose a specific way of distributing picture changing operators, this many number of picture changing operators, right? And in some other region in the moduli space, say here I have again similar world sheet. Since I use different notion for my odd coordinates in the supermoduli space, I have to use a different assignment of PCO distribution. So all over the moduli space I assign PCOs on the world sheet, but since I am doing the splitting of different regions, I am supposed to distribute PCOs in different ways in different regions.
But there are overlaps.
Overlaps. So that's actually another issue. So let me say why. Here I said that from the point of view of supermoduli space, since supermoduli space don't have a unique meaning for odd coordinate and even coordinate, we have to split the space into different pieces and then integrate out the odd coordinates in each pieces separately, right? And integrating out odd coordinates introduces picture changing operators, a specific distribution of picture changing operators.
And distribution is locations.
Locations. Say that's one situation.
When you go from one chart to another chart, you use transition functions like those.
Yeah, you have to do that. You have to do that. I haven't told you that. See, from this picture, you start seeing that you have to divide the moduli space into different regions and then assign picture changing operators in a specific way in each regions, right?
Is it unique?
It's actually not unique. So because depending on how you really split the supermoduli space, this splitting varies, right? So the usual notion of assigning picture changing operators is as follows. So you have one way of doing superstring theory, starting from super Riemann, get into super geometry and then do it. Or otherwise, what you have is something called picture changing formula, PC of so let me picture changing operator formalism of superstring theory. So you have PCO formulation of superstring theory and you have supergeometric formulation of superstring theory. You have two formulations. When you start from supergeometric formulation, you get the correct answers because you have reasons for doing everything. But when you do picture changing formalism, what you say is you only deal with Riemann surfaces and you have to only worry about the moduli space. Now what the price that you are supposed to pay is you are supposed to introduce some additional operators on the worldsheet. Introducing vertex operator itself is not enough. You are supposed to introduce additional operators, and the origin of that operator from the supergeometry point of view is the integration of odd supercoordinate. This is something one can explicitly work out and see. And the PCO formulation, the naive PCO formulation provided by Frieda, Martinek and Shankar says that you are supposed to introduce picture changing operator on the worldsheet, but it doesn't matter how you really choose distribute picture changing operator on the Riemann surface. You could distribute say 4 PCOs on 4 locations, here, 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 or you could distribute picture changing operator some other 4 locations. And their statement is that your final answer won't depend on how you distribute picture changing operator, right? So that's what they assume. So, but from the supergeometry point of view, you see that that should not be true. From supergeometry you could see. Now how that you can see that in picture changing operator formalism. In picture changing operator formalism, when I try to distribute PCOs in random ways over the whole region of moduli space, what you see is that you start seeing some extra singularities in your superstring amplitude, and these singularities don't have any physical meaning. You can't think of these singularities as a singularity coming from the collision of vertex operators. Collision of vertex operator corresponds to factorization of amplitude. So when you have a physical amplitude, you should see singularities only from the factorization channels. You are not supposed to see any singularity from some other source, right? All other singularities don't have any physical meaning. But here you see that when I introduce PCOs in a random way, you can calculate the correlation function for the picture changing operators and see that there are unphysical singularities that doesn't correspond to collisions of vertex operator. And the
singularities in poles,
you can see as poles in the amplitude
correspond to some non-physical,
which corresponds to non-physical thing. And you can really work out the details and see that they actually come from the fact that PCO distributions achieve some specific configuration. Whenever PCO distribution achieve a specific configuration, it's not necessarily collision. You can have collision for PCOs that will introduce a singularity, and that does not have any physical meaning, because anyway picture changing operator does not have any physical meaning itself, right? PCOs are something which we introduce. That doesn't have any physical meaning. Now you have another situation, PCO collide with the vertex operator. That can again introduce a singularity. Again, that does not have any meaning. Now the most severe singularity is something else. When I distribute PCOs in a specific way on the worldsheet, again you can see that even if they are not colliding with each other or with the vertex operator, still you can have singularity. So these kind of singularities are known as spurious singularities because they don't have any physical meaning. And that means over the whole region in the modular space, you are not allowed to choose any random PCO distribution. You should choose PCOs in a way that they avoid the presence of spurious poles.
Yeah, those poles like coinciding some coordinates in the denominator.
No, it's not just coinciding. It's a property of theta function. So theta functions can have they have zeros on the Riemann surface, and the theta functions can have so many arguments, right? In our situation, so when you compute the string amplitude, you see that those theta functions have arguments that is related to the positions of PCOs. Whenever that arguments achieve a specific value, theta function vanishes, and that does not have any physical meaning. So So that means you are not allowed to choose PCO distribution over the whole moduli space in a random way, unlike what Frieden and Shankar said. So from the supergeometry language, you see the similar statement. So forget about supergeometry for a moment. So we see that we are not allowed to choose PCOs in a random way. So the best thing is to do a splitting of the whole moduli space and then study whether some PCO distribution has zeros in this domain or not. Inside a specific region in the moduli space, you can do a local analysis and then see that a particular way of PCO distribution will provide you a spurious pole. Then avoid using that kind of PCO distribution. Don't use such a PCO distribution. Distribute PCOs in a region in the moduli space such that they don't have any spurious pole. So if I continue using that particular configuration all over the moduli space, they will start developing spurious pole. So stop at a domain and then choose another domain and distribute PCOs in another way so that they won't introduce any spurious pole. So you are bound to choose different domains in the moduli space. So even if you don't go back to your supergeometric formulation, you will be able to see the need of such splitting in the moduli space just by analyzing the PCO distribution.
No wrong distribution will give you finite results. Every time you choose a wrong distribution according to the supergeometry, will necessarily give you some divergence. What do you mean by wrong? So the supergeometry guides you to distribute in a particular way.
Yeah, that's true.
If you don't obey that rule.
Yeah.
If you don't obey that rule,
you will have. You will have a singularity.
That's a coincidence. That cannot be a coincidence.
That cannot be a coincidence. That's a perfect equality.
It is not done in a right way.
It's not done in a right way.
Is this rule that you mentioned, is it a result of some symmetry?
About the splitting of moduli space? No, actually it's not. I mean the maximum, the best answer you can have is from the supergeometry picture. Right, from the supergeometry picture you could see that it's very hard to distinguish between odd coordinate of the supermoduli space and even coordinate of the supermoduli space. That ambiguity will lead you to singularities in your superstring amplitude. So I mean you can't escape from a wrong thing. That's the power of superstring theory or theory. Whenever you do something wrong, theory will say that, oh, I have singularities, things are not working.
So is there a natural measure of the supermoduli space?
Natural
measure.
So that's what I said. That's what I said. You can construct the super Beltrami differentials and then define a measure on the supermoduli space, or at least a string measure.
You're going to use a top form.
Yeah, you have to construct a top form.
So when you go to the overlap, then the distribution is going to change continuously?
Exactly. So the point is that since I have since I decided to split the full moduli space into different domains, I can choose different PCO distributions in different domains. Now I have to make sure that these distributions matches on the boundary of the two domains, because I want a continuity for the PCO distribution. So that's another thing. So you should somehow match two PCO distribution over a overlapping region, and that is an easy thing to see from the point of view of supergeometry. So we can choose different patches in the supermoduli space and then choose a specific coordinate in each patches. Now whenever you have an overlap, you should find a transition function, right? So that transition function will induce a matching of two PCO distribution. That tells you how to match different PCO distributions.
So when you are integrating out the odd coordinates, are you basically rewriting that integration in terms of integrating over the PCOs?
It's not integrating over the PCOs. It's just introducing PCOs.
Within a single domain.
It's in a single domain.
PCOs should move then, because it is
PCO can move, right?
Can move means what?
But that means the locations of PCOs on the world sheet depends on the moduli parameter. When I move in the space of moduli parameter,
so it's not the supermoduli, the bosonic
moduli.
So on the bosonic, it will depend on the bosonic.
Exactly. So from the point of view of moduli space, any point on the Riemann surface, when I move in the moduli space, they move, right? You can't fix a point on the Riemann surface. When I move in the moduli space, they will move because the surface itself is moving, changing.
So then the PCOs are also corresponding.
PCOs will also change. The distribution will change in the moduli space when I go from one point to other. So that's a statement. Now if you are not someone who is interested in geometry, you can forget about this and then try to see is there any way to match the PCO distributions across a boundary of the two domains. And this is something which Ashok Sen introduced. So he called it a vertical integration. So he says that even if you have two different PCO distribution in two patches, you can try to match them by abruptly changing the distribution across the boundary of the two domains. You can jump from one configuration to another configuration, and he has a specific way of jumping, so which he calls vertical integration. So that's the way you matches two PCO distribution in two domains by performing a vertical integration. So you have a specific procedure for gluing two PCO distribution.
So that jump must be related to the exact location of the boundary.
Yeah, so you have exact location of the
boundary.
Yeah. So you can choose a region here and then jump in that region, or you could choose a single a codimension 1 boundary there and then jump or change the PCO distribution across that boundary. So you can freeze all your moduli parameters that's related to moving in this direction, and then suddenly change the PCO distribution.
Just to directly work with the moduli space.
You don't want to think in terms of supergeometry, right? You can go from supergeometry. Actually, Witten was trying to argue that it might be necessary to use supergeometry, because you see that there are unphysical singularities in your superstring theory or superstring amplitude. Somehow you have to get rid of it. So his reasoning was that you are getting into all this trouble because the world sheet is actually super Riemann surface and the moduli space is actually super moduli space, and super moduli space has a genuine supergeometry. It's not a rigid superspace. So you have to make sure that whatever you are doing is consistent with the fact that you have diffuse in the space, right?
This is one of the 200-page papers.
Yeah, so actually it's all set of papers were for clarifying this particular point. And then that time when he was writing the paper, what people know about picture changing formalism was borrowed from whatever Frieden and Schenger wrote long time back. They didn't have the idea that you have to choose different regions in the modulus. Actually, people had some idea. So they said that maybe you have to choose different regions in the moduli space and assign PCO distribution separate different way in different regions. But they didn't know how to match the PCO distributions across the boundary. So see, if you don't choose match the PCO distribution, that means you are producing boundary terms from different domains, which won't cancel each other. So to cancel each other, you have to introduce a vertical jump. So that your integration cycle becomes smooth. So he introduced this procedure. So and he called this vertical integration. Now, when I see that there are, say we have three domains, domain 1, 2 and 3. So I can choose a particular PCO distribution in domain 1 and 2 and 3 and try to match the PCO distribution in domain 1 and domain 2 across this boundary. I can do a vertical jump and match it. Here again I can do a vertical jump and match it. So this is vertical jump 1 A. Here I can do a vertical jump B, and here I can do a vertical jump C. Now when I go to this point, vertical jump A, vertical jump B, vertical jump C may not match together. So there again you have to do further correction. So this is something which was pointed out by Witten, and then together Witten and Sen clarified all these issues, and then they found a systematic algorithm for distributing PCOs over the whole moduli space by jumping or changing your PCO distribution across codimension 1 boundary, codimension 2 boundary, codimension 3 boundary, and goes on. So the way you distribute PCOs is actually not that simple. So one has to be very careful when you compute superstring amplitude. First of all, you have to start with a specific distribution of picture changing operator over the whole moduli space. So
if you are working with the super moduli space where you have an overlap, then there is no jump. It is continuous.
You can make it continuous jump. So here also you can make it make your jump continuous. You can do it. So but the point is that the most surprising thing is that you can just do a jump. You don't have to do it in a continuous way. So that's like a surprising thing, and that's more convenient to do. So anyway,
Principle is not to introduce Spurious poles.
in principle,
The principle
is to avoid the spurious pole. Exactly, not to introduce a spurious pole. And the final amplitude,
diagnosis to do.
this is the only diagnosis to do.
So you can say, avoid spurious poles, but practically, is there
So the reason why I am saying this is only way is the following. See, the supermoduli space, there are some situations where you can uniquely or without any ambiguity, you can split odd coordinate and even coordinate. So whenever you have low genus computation, whenever you have a scattering process in which you only care about lower number of handles and lower number of punctures, one can see that this splitting is possible. You can split the supermoduli space into moduli space and an anti-commuting space. Whenever that is possible, you can integrate it out. And that was one situation which Docker and Fong considered. When they computed two loop amplitude, they realized that at least in that case, you can actually split the moduli space into two, and depending on what kind of spin structure that you use, whether you are using even spin structure or odd spin structure. My understanding is that they studied even spin structure, which is much simple compared to the other. So in that situation, you can integrate out. Then you can say that I can do that integration, and then I don't have to really worry about all this vertical jump. In that situation, you will see that you won't introduce any spurious pole. But
you have one single cover of the.
You can choose a global coordinate and then integrate it out. But in the other situation, you don't have any. You can't do it, because there is a theorem saying that when the number of genus and when number of punctures are large enough, then it's impossible to split the two coordinates, even an odd coordinate. That means the moduli space, supermoduli space won't split.
How long? How much is the genus?
If there is no puncture, I think above genus 5, definitely you can't split it. Genus 4 or 5. And if I
Genus 0 and how many punctures?
That number, they don't have any fixed number. So they say that I don't really remember. I think their statement was not very rigorous, saying that exactly when you have this particular genus and with this number of punctures, you don't have split. That's not the statement. Above some number of genus and punctures.
We have said that something 6
Who?
punctures itself we see a problem of genus 0.
See, you can see that naively from the fact that whenever you have enough number of odd coordinates in the supermoduli space, you have difficulty, right? So anyway, that's one thing. So this itself says that if you want to compute amplitudes in superstring theory, you have to be very careful about picture changing operator. This is one aspect, and I won't really I won't discuss anything more about this particular aspect. Now the next thing is that I said that you have to assign picture changing operators or distribute picture changing operators on the world sheet, right? Now what next condition is that when I do a mapping class group transformation on the Riemann surface, when I do a large diffeomorphism, then the distribution that I introduce may change, right? So the PCO distribution that I started with may change when I do a large diffeo transformation. So such a thing is not a nice thing, right? Because anyway, we want to construct a differential form on the moduli space. A differential form on the moduli space should be invariant. We should be able to find a distribution of PCOs that is invariant under MCG transformation. Invariant under MCG transformation. So that's a challenge too. So first challenge is that we should find a way to integrate over the moduli space. Second challenge is that we should, so challenge 1, integrate over moduli space. Second is that find MCG invariant distribution of PCOs. So you have two extremely challenging problems. you have two problems that we should solve before writing down a superstring amplitude. Only if we can solve this thing, we can finally get a number for superstring amplitude. So if you want, you first construct your superstring measure by using all this Beltrami differential idea, and then by choosing a PCR distribution that is invariant under mapping class group transformation. And then we should know how to integrate that string measure over the whole moduli space. So these are the two problems.
Are these systems sequential?
Sequential in the sense, first actually is actually in this way. So you have to, right.
I was wondering whether, if the PCO distribution is mapping class group invariant.
Yeah.
Are you guaranteed that there are no spurious singularities?
No. The spurious singularity is another thing. That's why I said I won't discuss anything more. So spurious singularity situation is one thing that anyway we have to handle. On the top of it, we have another challenge which usually people don't talk about. People hardly say that you have to choose PCR distribution in an MCG invariant way. If I don't choose PCR distribution in an MCG invariant way, I'm not actually constructing a differential form on the moduli space. I'm constructing a differential form on the Teichmuller space.
If you go supermodular space way,
yeah,
it will not automatically.
No. There also I have to worry about the mapping class group.
Yeah.
So my final statement is this thing. Today, the final statement is that I have to solve these two problems to write down superstring amplitude. And my statement is that these two problems can be solved in a single step. In one single step, I can solve these two problems and then obtain. Yeah.
Yes.
Yeah. Yes. Yeah. So this
Point at the end of the lecture.
Yeah. Yes. So this is what.
So you are going to write the third string theory.
No. So that's it.
So is it known